Welcome back, Rashid here with another topic on RTL2 routing series. In the last video, I talked about logical and timing optimization. Today, I'm going to finish that with some additional discussion on area and DRC, and then I will look into different compile or synthesis stages. Okay, so area. So we have overall, if you remember the time, overall the constraints that that design works under, or the constraints under which we do physical design, are what? Timing constraints. Okay, then floor plan constraints, right? Then power constraints. But timing and floor plan are extremely critical. Shouldn't say that. I think everyone is critical. It depends on your application, your design, and what is your really target market, and what are your challenges with the current die. So, area is overall a floor plan. Sometimes I call it area. Basically, your block needs to be contained in a certain area on a die. So it needs to consume a certain real estate on the die. Okay. Um, if it is too big, could be a problem. Too small could be a problem. If it's you typically want to hit a certain utilization. So your goal is you consume the area so efficiently that you don't waste the real estate of die, right? The die area, that real estate on the silicon real estate is super expensive. You don't want to waste that. Okay, and if you have too much area to start with, tool eventually cells gonna be spreading, and then in order to do that, tool is going to add a lot of buffers and inverters, right? If the to hit a to make sure it hits certain transition time and capacitance and all that. So your area needs to be optimal. But if you pick a very tight area, eventually what's going to happen, you may end up consuming most of the space later on during your synthesis. You don't have much left for later on CTS or hold fixing and all that. But at the same time, if overall your structure, your design structure is such that you have a lot of wiring going on, okay, and keep in mind that wiring is also going to be in the similar area, and a certain area contains certain number of metal 1, metal 2, 3, or whatever metals you have. It contains certain routing tracks, okay, places where each metal can go, and that is also constrained. Okay, you need to follow certain metal to metal spacing. You need to follow certain minimum width of the metal. So considering that in mind, you also have a certain number of wire resources that you can use. So you want your area such that you are able to connect all the devices together, okay, and at the same time you don't get too much overhead of buffers and inverters. Okay, so a lot of different techniques of different very fundamental type of things tools can do. Some of them are listed here. So for example, we can use smaller cells. Okay, this is not the same slide I had. Okay, anyway, I have to draw something additional here, which I thought I already drew. But smaller cells mean what? Okay, if you remember from CMOS fundamental, your size of the cell is what? Your width, its width, and its length. Okay, and the current is proportional to W over L. So the length is fixed, right? There is a particular technology, so your length of the channel, length of the transistor, is the minimum is fixed. You don't want to increase that. You don't want to have a mix of different length of transistors. But what you can do is you can play with the width. Okay, so you can increase the width to increase the current. And when you increase the width, means you will have bigger transistors, When you have a bigger transistor, means you have bigger standard cells. Okay, so you can have, in the standard cell library, you can have inverters, buffers, NAND, and all those cells with a different width or with a different size. Okay, so if it's timing critical, you want to pick a bigger size cells, right? Because they will have higher current, they can work at high frequency. But if it's tighter for area, you have to use smaller cells. Make sense? Then the other thing is relative placement of the cells. As I mentioned earlier, cells are placed with respect to relative to each other. Okay, so if for a smaller area, tool will shrink the relative placement of the cells. And then in order to avoid congestion, tool sometimes has to spread it. So within a certain area, you don't want to clamp too many cells at one place. Based on a logic, their interconnection, that might be a problem for routability later on. Then some other constraint also come, okay, where you want to place your pins, where you want to place your macros. Macros play, actually all these play a super important part, because they're gonna, macros position depends on the timing interface to macros, and that can have an impact on the area of the chip, because typically, for example, SRAMs will be pretty big compared to standard cells. So they can really contain the area for standard cells. And you don't want to put SRAMs in the middle, right? You have to put on the side. So there can be a lot of challenges, but those are part of the area floor plan optimizations that tool can do itself, or you can help the tool by giving a certain placement of the macros. You can help the tool by, if you already know your design, you know the flow of the data, you know certain ports, or what I'm calling here pins, the ports of the design needs to be on this side, because they go to SRAM first, or your SRAMs are placed first, and your other logic is go. So, you need to understand kind of higher level flow of data in your design, and based on that, you can drive floor plan and hence area. Voltage area, VS voltage area. In a design with a lot of different power domains, you need to define voltage areas where cells belonging to particular domains need to be placed. And you don't want to mix them, because over each voltage area you will bring the required power grid. Okay, so a lot of things to talk about, but the bottom line is area is an important consideration during synthesis, and tool is going to do a lot of optimizations that it can do, and it depends on what is your highest requirement, right? Is it a timing? Do you want to meet timing at the expense of area? Is that good or not? Or the area is your biggest stuff and you can reduce the frequency? It depends on that. Another important timing, I should have put this under timing, but typically it's put separately, DRC. So these are electrical DRC, right? These are not physical. These are not, I'm not talking about the layout design rule constraints. I'm talking about electrical design rule constraints, and those are the capacitance and the transition time and the fan out. So keep in mind that these are the constraints, not the actual values, right? So actual values, for example, if you have a design, okay, this goes to, let's say, flip-flop, from here goes to N, another N goes to another flip-flop, and thus goes out. Okay, so you have two ports, input and output, and you have different nodes internally. Okay, so you apply a transition time. That is the constraints you give at the port. Okay, I'm not talking about that one. So you're applying a stimulus, say you're saying on this port of my block, you know where it's coming from, it will have 100 picoseconds. So you apply 100 picosecond here, and you put an output. Let's say you know the output side connection, so you think that, okay, it will have 10 femtofarad capacitance. Okay, so you apply those, and what tool does is tool propagates those. Okay, so it moves this. This is the wire. It knows how much R and C it has, so it moves that and determines how much transition time here. And then it also determines the capacitance of this one. Then on this one, and I already talked about this during the timing, but it determines capacitance here, transition here, capacitance, transition in each node. So this is the constraints that we are talking here, is the max capacitance and max transition on any node in the design. Okay, so if you put maximum transition is 30 picosecond, and tool moves this 100 picosecond, and there's another wire here and reaches here. Since you're giving 30 picosecond, it sees that you need to ensure that entire node, a transition time when it reaches here is 30 picosecond. So what it's gonna do is gonna put inverters or buffer it, so it doesn't change the functionality of the design, but at the same time the drive, it's gonna put more devices there to drive this transition time to a lower value. So that's why by setting a higher lower, tighter max transition time, what can happen is tool might end up putting a lot of buffers there, and that sometimes may result in a better timing, may not result in, because it also comes at the overhead of additional cell delays. So transition time and the max capacitance, same thing. You're saying, okay, what is the maximum capacitance a node can drive? So if you apply a very aggressive value here, tool will see, no, this is too much. So it's gonna add more side, it's gonna bring cells closer and all that. So and the fan out, the fan out is the same. So fan out is if you have this buffer and it's driving 3 buffers, because each of them goes to maybe different flip-flops or something like this, right? So what is the fan out of this one is 1, 2, 3. Okay, how many load capacitance it has. And also, of course, this more fan out means what? More fan out means more capacitance here, right? Which will decrease the transition time. So this one is related to kind of this one too. So if these two, the values that you give to them can have a bigger impact on your overall cell count, on your timing, on your area. So it's very important that as you are creating recipe for your block, you play with different values of max trans, max cap, and see which one gives you the best QR, right? And in order to add, as I discussed that, okay, tool can do cell sizing. It can vary the size of this cell. It can put a different inverter because it's going to 3 of them. It can add buffers there, as I just mentioned there. And the placement, it can move sometime. Okay, this flip-flop is too far away. I cannot meet the mass transition or capacitance, so let's bring this closer to it. It can make those decisions. All right, I think that's it for now. In the next video, I'm going to talk about the different compile stages and at what level at what stage I'm using different optimizations or different compile stages in the overall synthesis flow. So I'll talk about those in the next video. So, but that's it for now. See you next time. Bye.